From ancient beliefs that placed Earth at the center of everything, to the mind-bending theories of space and time, this is the story of how we came to understand our place in the universe. Travel through the bold eras of discovery, from flat Earth to heliocentric revolutions, from Newton's laws to Einstein's relativity. Meet the dreamers, rebels, and visionaries who dared to question the skies above. This is more than history. It's a cosmic odyssey through human curiosity, science, and the relentless pursuit of truth. Welcome to the full journey of how we discovered the universe as it truly is. Our journey began with one of the earliest cosmic debates, the clash between the flat Earth belief and the idea of a round Earth. In ancient times, people believed the Earth was flat because, to the naked eye, it appeared to be a vast flat surface, stretching endlessly in all directions. Without the benefit of modern scientific tools or the understanding of astronomy and physics, this simple observation shaped their worldview. Although the ancient scientist Aristotle got many things wrong in physics, he was one of the first to suggest a groundbreaking idea for his time that the Earth is round, not flat. It's hard to say exactly what evidence led Aristotle to his conclusion, but we can identify several key observations that likely influenced his thinking. Evidence 1. By observing ships as they sailed away, people noticed that the hull would disappear first, followed by the sails. This phenomenon provides clear evidence of a curved surface, something that can only happen on a round Earth. If the Earth were flat, both the hull and sails would vanish simultaneously from view, not in sequence. Evidence 2. During a lunar eclipse, we can see the Earth's shadow cast on the moon, and it's always round. This consistent circular shadow can only be caused by a spherical object. If the Earth were flat, its shadow would appear as a line or have different shapes, not a perfect circle. This is strong evidence that the Earth is round. Evidence 3. As travelers move north or south on Earth, they notice that the stars in the night sky change gradually. Some stars that are visible in the northern hemisphere disappear below the horizon when heading south, while new stars appear in the southern sky. This shift in the star patterns can only be explained by a curved, spherical Earth. If the Earth were flat, the same stars would be visible from all locations, regardless of direction or distance traveled. With nothing but observation and logic, Aristotle made a bold claim. The Earth is not flat, it's a sphere. There are many other pieces of evidence as well, but one of the most remarkable comes from a librarian of Alexandria named Eratosthenes. Over 2,000 years ago, the Greek scholar Eratosthenes made a remarkable discovery. He not only demonstrated that the Earth is round, but also calculated its circumference, using nothing more than shadows, a stick, and simple geometry. In Egypt, there is a city called Syene. Eratosthenes noticed that in Syene, on the summer solstice, the sun stands directly overhead at noon, so much so that a vertical stick casts no shadow at all. But at the very same moment in Alexandria, another major city of Egypt, a stick does cast a shadow. This difference reveals something important. The Earth's surface must be curved. If the Earth were flat, shadows would appear the same at the same time in different locations. But we see shadow in Alexandria, but not in Syene. As a result, we can say that Earth is curved. The angle of sunlight changes depending on where you are, causing shadows to differ. Now, how he measured the circumference of Earth, basically he measured the shadow in Alexandria. It was about 7.2 degrees. That's roughly 1/50th of a full circle. Eratosthenes also knew the distance between Alexandria and Syene. It was about 5,000 stadia distance. The stadia was an ancient Greek unit of length. Now multiply that by 50 to estimate the entire circumference of the Earth. That would make it 250,000 stadia. This measurement was about 2% off from the actual value we know today. Today, we can confidently say that the Earth is round, or more precisely, spherical, based on overwhelming evidence. From satellite images taken from space to scientific measurements and centuries of observations, all confirm that the Earth is not flat, but a sphere. Yes, Aristotle was right about the Earth being round, but he also made some mistakes. Let's learn more about this. Explore some of Aristotle's key misconceptions that prompted a major transformation in the foundations of modern physics. Although Aristotle played a tremendous role in the development of metaphysics and science and philosophy, most of his ideas were later proven wrong in physics. He believed that the Earth was made of 4 elements: water, soil, air, and fire. However, we now know that it is made of atoms, protons, neutrons, electrons, and more specifically, quarks. He also claimed that objects stop moving because they seek their natural place, but we now know that friction is the true cause. Aristotle argued that heavier objects fall faster than lighter ones, but in reality, both fall at the same rate. Lastly, he insisted that the Earth is the center of the universe, which was also later proven wrong. As Aristotle and many ancient scientists believed that the Earth was at the center of the universe and everything else moved around it in perfect circles. Supporting the belief, Aristotle and other ancient thinkers, Ptolemy, a mathematician and scholar, gathered the observations of earlier astronomers and used his mathematical skills to develop a model, placing Earth at the center of the universe and explaining the planet's movements. Ptolemy's model was incredibly complex, especially with the introduction of epicycles, smaller circular orbits within larger ones. We can visualize these paths with diagrams, showing how the planets moved in these intricate circular orbits. But scientists and philosophers started to question, why should the Earth, or any planet, follow such complicated and unnatural paths? Then, in the 16th century, a revolutionary idea emerged. Nicholas Copernicus, a Polish astronomer, challenged Ptolemy's model by proposing a radically different view, that the sun, not the Earth, was at the center of the universe. Copernicus knew that the sun was the main source of energy, and placing it at the center not only made more sense, but it also solved the problem of epicycles. The complicated paths that planets followed in Ptolemy's model vanished. This was the beginning of the heliocentric theory, which would change the way we understood the cosmos forever. So, after 1543, 2 major theories emerged: Aristotle and Ptolemy's geocentric model, and Copernicus's heliocentric model. After that, Galileo was the first to prove that Copernicus's heliocentric model was correct using his own telescope. One night, while observing the moon through his telescope, he noticed cracks and craters on its surface. This proved that heavenly bodies are not perfect, its features similar to Earth's surface. After that, he discovered 4 moons orbiting Jupiter. As they moved around Jupiter and not the Earth, it proved that not everything in the universe revolves around the Earth. Then he observed Venus and noticed its phases, patterns of light and shadow. These phases could only be explained if the sun, not the Earth, was at the center of the solar system. From Earth, the changing phases of Venus appear like this. Thus, Galileo confirmed that the sun is at the center of the universe. Then another scientist named Kepler came along. Although he and Galileo lived around the same time, they never met each other. Both independently proposed that the sun, not the Earth, is at the center of the universe. Kepler was the first to formulate 3 laws describing the motion of planets based on Copernicus's model. He developed these laws using 18 years of Mars observations recorded by his teacher, the renowned astronomer Tycho Brahe. His first law is the orbit of a planet around the sun is an ellipse, with the sun at one of the 2 focus. An ellipse means a stretched out circle, like the shape shown in this diagram, and it has 2 focal points, and the sun is located at one of them. His second law is a line joining a planet and the sun sweeps out equal areas in equal intervals of time. This means that the velocity of planets is not uniform. It changes at different points in their orbit. When a planet is near the sun, its speed is much higher, and when it's farther from the sun, it moves more slowly. In the figure, we can see the bided time. When the object is closest to the sun at time t, it covers a greater distance. On the other hand, during the same time interval t, it covers a shorter distance elsewhere. However, the areas swept out in both cases, shown by the green shaded regions, are equal. His third law is the square of the orbital period t of a planet is directly proportional to the cube of the radius of its orbit. Suppose from the figure Mars and the Earth's period is t1 and t2, if their radius is r1 and r2, then t square proportional to r cube in the quiet countryside of England. under the shade of an apple tree, a young Isaac Newton sat in deep thought. It was the year 1666. The world was gripped by the Great Plague, and universities had closed. Newton had returned home, unaware that this isolation would give birth to one of the most powerful ideas in science. Legend has it, and perhaps embellished over time, that an apple fell from a tree landing near him. While it didn't strike his head, it sparked a profound question in his mind. Why did the apple fall straight down, but the moon doesn't? From that simple question, Newton began to form a revolutionary idea: gravity, a universal force that pulls objects toward one another. Whether it's an apple to the Earth or the moon in its orbit, gravity is everywhere. Years later, Newton would mathematically describe this force in his law of universal gravitation. Every object in the universe attracts every other object with a force that is proportional to their masses and inversely proportional to the square of the distance between them. Here, m1 and m2 are two masses, and d is the distance between them. So by Newton's law, we can write F equal to g into m1 into m2 divided by d squared. From Newton's law, we know that F equal g m1 m2 divided by d squared. Now, as F is the centrifugal force, we can write m into v squared by r. Again, v equal to omega r and omega equal to 2 pi by t. If we calculate further, then we get a relationship between t and r. It is t squared proportional to r cubed. And this is the third law of Kepler. Newton shows that we can derive Kepler's third law from my equation, which confirms that the equation is correct. Not only that, he also invented calculus to describe the motion of planets. Later, calculus evolved into its own branch of mathematics. Oh, we can say that Newton had two powerful tools. One was calculus, and the other was his law of gravitation, from which Kepler's laws could be derived, which is basically observed value. Newton's law of universal gravitation was accepted because it successfully explained a wide range of natural phenomena. It accurately predicted the motion of planets, moons, and falling objects on Earth. How can a planet keep moving in space while an apple falls to the ground? Newton illustrated this with his famous cannonball experiment. Now, imagine firing a cannonball straight out, parallel to the ground. If the cannonball moves slowly, it falls to the ground nearby, pulled by gravity, just like the apple. A huge cannon sitting high above the clouds on a very tall mountain. Now, firing a cannonball again straight out, parallel to the ground. Then, fire it faster, and it travels farther before hitting the Earth. But now, imagine firing it at such a high speed that it never touches the ground. It's continuously falling around the Earth. This simple thought experiment, Newton's cannonball, explained both why apples fall and why planets move. So, in one word, there is the initial velocity of planet, that cause of moving the planets. What is the required velocity for an object to maintain circular orbital path? Let's calculate this. We know if the centrifugal force is equal to the gravitational force, then this moves in the circular path. So Fc is equal to the Fg. We know Fc equal half mv squared by r and Fg equal gmm by r squared. If we cut mr and then v equal root over gm by r. If we put the value of Earth's value of m and r, then the value will be 7.88 kilometers per second. Then there is another term called escape velocity comes. It's the minimum speed needed to break free from gravitational pull. It is a special kind of velocity for Earth. It is 11.2 kilometers per second for Earth. So how this 11.2 kilometers per second comes? Let's explore this. We know gravitational potential is the potential energy 1 kilomass at a point in a gravitational field. From the gravitational potential law, we can write V equal to minus gm by r. Now, if we do opposite of that, means 1 kilomass into the infinity from gravitational field, and we know this is called escape velocity. So the equation will be plus gm by r. Now, if it is mkg of mass, then the equation will be gmm by r. As V is basically work, it is fully kinetic energy, so V equal half mv squared. If we further calculate, we can write VE, or escape velocity, will be root over 2gr. For Earth, it will be 11.2 kilometers per second. So there is two important velocity. One is orbital velocity, 7.88 kilometers per second, and another velocity is escape velocity, which value is 11.2 kilometers per second. Now, detailing of cannonball experiment. When the speed is less than 7.88 kilometers per second, the Earth appears at the far focus of the orbit. When the speed is 7.88 kilometers per second, the orbit becomes circular. At a speed of 7.88 kilometers per second, the satellite enters a stable circular orbit around Earth. If the speed is greater than 7.88 kilometers per second and less than 11.2 kilometers per second, the Earth appears at the near focus of the orbit. When its speed is equal to 11.2 kilometers per second, or equal to escape velocity. Actually, it is the minimum speed required for an object to escape the gravitational pull of a planet, and the path becomes hyperbolic. If the speed is greater than 11.2 kilometers per second, then it takes the path of parabola. Newton's law of gravitation is so powerful that whether on Earth or in space, it consistently holds true. But soon, a problem emerged. In 1781, William Herschel accidentally discovered Uranus. However, when astronomers measured Uranus's orbit, they noticed it did not follow Newton's law of gravitation. Some deflection could be observed in its path. This led to two possibilities. Either Uranus did not obey Newton's laws, or there was another unknown planet whose gravity was causing the deflection. To solve the mystery, French scientist Urbain Le Verrier used mathematics to predict the exact location where a new planet must exist to account for the observed changes in Uranus's orbit. He then sent this information to an astronomer in Germany. German astronomer Johann Galle pointed his telescope at the predicted spot, and there he found a new planet, Neptune. It became the first planet to be discovered through mathematical prediction, and once again, Newton's law of gravitation was proven correct. After that, Newton's law of gravitation gained widespread recognition because it helped discover a whole new planet. Even after all this, Newton's law is not entirely correct. One major issue is Mercury, as its orbit shows a precession that Newton's law couldn't fully explain. Orbit precession, we can see it in the figure. Some scientists thought the precession was due to the gravitational pull of an unseen planet, which they called Vulcan. It was later proven that there is no planet called Vulcan. There was also another problem that Newton himself mentioned. How can two masses influence each other across a large distance? For instance, the Sun and the Earth are far apart, so how is gravitational interaction possible between them? Newton himself was not fully satisfied with his theory for this reason. He once said, "I know my equations work, but I do not know how they work." It is possible that scientists in the future will find a solution to this problem, but now we know that Newton's laws are unable to explain many phenomena, such as black holes and other complex cosmic events. We will solve this problem later as we continue our journey in Part 2. If you want to see Part 2, write Part 2 in the comments.